Okay. Do you have any questions from previous classes, previous seminars, anything? Okay, so this is the seminar number 16. Today is the 13th of October. All right, so I guess that this is not the last seminar, but it's the last seminar in which we do new things. Even the next seminars in which we will solve the triple integrals, I think, even them, even those, I mean, will be essentially repetitions of what we have done so far. There is nothing new in triple integrals that has not been done um, in double integrals. So today we are going to see application of the change rule for double integrals, and we are in section 4 of chapter 14. Let's see then. If you have no questions, I'll start. So we have exercise 14.4.5. We have this double integral x squared dx dy. And now the domain is a disk of radius a, right? So I mean, change of variables is change of coordinates is the usual thing that you did in one variable too. You change the variable to simplify your expression, and in this specific case, I think um, that a good idea might be to use the polar coordinates, for instance. So using changing the variables, change of variables. You set as usual r is equal to x is equal to r cos theta, and y is equal to r sine of theta. R is positive and theta belongs to 0 to pi. Um, right. So the formula for changing the variables tells us that I is going to be equal to the integral, the double integral of d. Now this d, maybe I should write r theta, because dr theta is d, but written in polar coordinates. Specifically, if you want, dr theta is going to be equal to the set of the r theta belonging to 0 plus infinity times 0 to pi, such that r is less or equal than a. Right? So this is the disk. And we change the variables, so we substitute to x what we have. So we have r squared times cosine of theta squared. And now you have to remember that in the one variable you had the differential. So here we have to multiply also by the modulus of the Jacobian of the transformation, and this is going to be r, right? This is Jacobian. Don't forget the Jacobian. Jacobian of the transformation. Which is R, and it is R because we have seen that already. Um, if you remember at some point, I think we were doing implicit function theorem exercises, and we have seen the transformation, the polar transformation, and I told you, remember this Jacobian because it will be very important. And that's why it is very important. Because, yeah. Okay, and then this will be the R d theta. So what is this now? This is the double integral. We have no limitations on theta, so theta will be 0 at 2 pi, and 0a on r. So this is r to the power of 3 cosine squared d r d theta. Okay, I go maybe to the next page. So this is. So now you have that star, and this is equal to 4a this, and this, cosine squared d this. And what is this now? A to the power of 4 divided by 4. I'm using the double angle formula. This is 1 plus cosine of 2 theta divided by 2 in d theta. And this is giving me a to the power of 4 divided by 4 times 1/2 times theta plus sine theta cosine theta between 2 pi and 0. And this is equal to pi times a 4 divided by 4. This is the result. So, do you have questions about this? Okay, number 9. What's the exercise number 9? What do you mean? Okay, so we want to compute double integral over d of e to the power of x squared plus y squared dx dy, where d is now not only, I mean, not the complete disk, the entire disk, but we also pick x and y positive. So this is the portion of the disk in the first quadrant, right? So it's this part here. Okay, so if you write this domain in the polar coordinates, this is going to be equal to r less or equal than a. But then here we want also x and y positive, so we have to pick the angle such that so this is going to give us theta less or equal than pi divided by 2 and greater or equal than 0. So this is what we have. If we change of course, the variables in polar coordinate, but this is essentially screaming for change of variables in polar coordinates because we have e to the power of the radius squared, and then we have a domain which is essentially a disk. So we have that I is therefore equal to integral this, and then we have e to the power of r squared, and then we have r here. Remember the Jacobian, and this is theta. You could actually integrate in theta directly. You get pi divided by 2, integral between 0 and a, as this, the r. And this is, of course, equal to e to the r squared divided by 2 between a and 0. And this is pi divided by 4 times e to the a to the power of 2 minus 1. So it's not too hard to do, at least for simple integrals. Then it might get messy if you have maybe harder integrals. So let's see this 14.4.11. We have I, which is double integral over d. Now the function is x plus y, dx dy, and so now d is x squared plus y squared, this, and the book says under the line y equal to square root of 3x, first quadrant 2. So we want x positive, y positive, and y below the square root of 3x. So this is slightly more complicated than before. Slightly. We have a straight line here. We are in the first quadrant. We are within the disk, and we are below the straight line, as I said. So it's this portion here. Okay. Now, what is dr theta if we want to use polar coordinates? So dr theta is going to be equal to, again, r is less or equal than a and supposed to be positive, so on. And theta is between 0 and this time, instead of pi divided by 2, we are just up to pi divided by 3, because that's tangent of pi divided by 3 is equal to square root of 3. So we get that straight line. So also this one is very easy. We get this is equal to double integral between 0 and pi divided by 3, 0 and a of r cosine theta plus r sine theta in the r d theta. No, but I forgot the Jacobian. That's why I'm telling you don't forget the Jacobian. The r d theta. We can integrate in r directly, and we get a to the power of 3 divided by 3 times the integral between 0 and pi divided by 3 of cosine plus sine in theta. So what do we get here? So this is equal to a to the power of 3 divided by 3 times sine of theta minus cosine theta between pi divided by 3 and 0, and this is equal to a to the 3 divided by 3 times square root of 3 divided by 2 plus 1/2. And that is the result of our calculation. Can write, yeah. Okay. Let's see the number. Well, let me try. I thought it was stupid to change the variables in this number 13 because it's easier to do in Cartesian coordinates. That's another thing of this book. So the integral to be solved is the integral between, no, over t. T will be a triangle of this function here. T is the triangle, not triangle, triangle. Let's see, with vertices 0, 0, 1, 0, and 1, 1. So it's this triangle here. Yeah. So if you compute, if you in Cartesian coordinates, this triangle is very easy to express actually. This is, let's say, x between 0 and 1 and y between 0 and x. So if you want to integrate this integral directly, it's pretty easy. Let's see what happens. So easy if you don't change variables. The variables. Let's see what happens when you change the variable. Okay, so if we use in polar coordinates, what is d? What is t? T is equal t of r theta. This is equal to, okay, so I guess the angle will be between 0 and pi divided by 4. So theta is between pi divided by 4. And r will be a function of theta in this case. Let me see. Let's see. Well, okay, so this is constantly equal to 1. I guess we need to so r is equal to what? If we have like a triangle like this and this is theta, some triangle things. So I guess that no, it's not between 0 and 1. It's a function because it would be between 0 and 1 if it was a disk, but now it's a triangle. So the radius will be depending on the angle, and we need to use these theorems that now I don't remember on the triangles. So what the hell was? I need to look in the book. Yeah, I mean, I need to multiply. I don't remember if it is cosine or sine. It should be something. I mean, this. Just let me check one thing because I don't remember if it is sine or cosine. Uh, okay, so what? this is not what I'm looking for. Yeah, it's sine. I never remember this. Okay, so sine is the opposite and the cosine is the adjacent divided by the hypotenuse. So r will be equal to uh, r times cosine of theta is going to be equal to 1. So r is equal to 1 divided by cosine of theta. Let's see, for cosine, for theta equal to 0, we have 1, and for theta equal to pi divided by 4, we have square root of 2 divided by 2, which is, yes, square root of 2. So that this seems correct. So r is between 0 and 1 divided by the cosine theta. Sorry, I got lost for 1 second. So yes, so this is yeah, I basically solved this triangle here that I'm painting in black, right? If this, and now it sucks. Um, okay, so if you have a triangle here, and now you know that you have some angle theta here, you want to find the radius, and this radius has to be a function of theta, right? So you need to use the trigonometry here, and the theorem that tells you what's the relation between hypotenuse and the other edges of a right triangle. It's this one that I wrote here. So now we have the correct endpoints. We can write that I is equal to the double integral between 0 and pi divided by 4, and then we have 0 and 1 divided by cosine of theta, and then we have r squared times r, which is the Jacobian, d theta. We cannot integrate in theta first. So what do we get here? We get this. Oh Jesus, this is 1 divided by 4, and this is 1 divided by cosine to the power of 4 in d theta. I wonder if this has some nice integral. Hmm. Mm, I guess that one could. Well, I don't know how to compute this integral here. Now I don't see that immediately. But the result should be, let me think 1 second. The result is 5 divided by 12. Uh, well, okay. I guess you can. I guess one could write 1 divided by cosine to the 4 as, so if I use cos squared plus sine squared divided by cosine to the power of 4. So this is 1 divided by cos to the power of 2 in d theta plus tangent squared times 1 divided by cos squared in d theta, right? And now this should be the derivative of the tangent, right? Yes. So this should be tangent of theta plus, and this is again tangent to the power of 3 divided by 3 plus a constant. So this should be correct. Yeah, you can do that. You can do a change of variables. This should be okay. So this is correct. So yeah, you fill in the details, but this is how it is. Okay, so you see that this complicates much. I mean, a change of variables not doesn't solve the problems always. I mean, in this case, it would have been much easier to just integrate. That's a polynomial. So you have to be careful when you change the variables. It's not going to lead you to something easier necessarily. Okay, so let's see the number 15 then. We want to find the average distance from the origin to the points in the disk. Blah blah. So find the average distance from the origin to points in the disk x squared plus y squared less or equal than a to the power of 2. So what's the okay, so we have seen already how to compute averages, right? And we have seen how to compute averages of some functions. So now we don't have a function apparently, but it says the average distance. So this word is not very well written. Disk. So it says average distance. So this is the keyword, the distance. What's the distance function? So the distance function to the origin is f of xy equal to the square root of this, right? That's Pythagoras. So we want to find the average of this guy here, of the disk. Let's see. We're interested in, first of all, to compute the integral. Now this is the disk of radius a. And the function is this one, dx dy. Now here we can use the polar coordinates. So we get between 0 and a, between 0 and 2 pi. And this is r times r in the r, no, d theta dr. So you get 2 pi times a to the power of 3 divided by 3. So this is the integral, but we were interested into the average. So we have seen that average will be I divided by the measure of the disk. So this is so area of dA. So this is equal to 2 divided by 3 pi a to the power of 3 times pi divided by a to the 2. So this goes away. this goes away, and we get that the average distance is this. Okay. Let's see number 21. It says, find the volume lying between paraboloids. Lying between the paraboloids z equal to this right? Okay, so we have to find out, so we will have some paraboloids here. It will be something like this. And we want to find the volume. They will intersect somewhere here. So let's first find out where they intersect. So intersection between them. Intersection will be solving the nonlinear system, z equal to this, 3z equal to 4 minus x squared minus y squared. You just set things to be equal. You get that this leads to x squared plus y squared equals to 4 divided by 3 minus x squared divided by 3 minus y squared divided by 3. And then this is equal to x squared plus y squared equal to 1. So in intersecting this circle, and this is going to be our domain, right, of integration. So this means that the volume is going to be equal. Let me call this, yeah, no, let me call this nothing. So the volume will be the integral over x squared plus y squared less or equal than 1 of what? Of the upper paraboloid, which is 4 minus x to the 2 y to the 2 divided by 3 minus this in dx dy. This would probably be quite hard to compute without the change of variables, but with the change of variables should be easy. So we do the change of variables, so polar coordinates, and we get the integral between 1 and 0 and 0 to pi of what? Of 4 minus the radius squared divided by 3 minus the radius squared times the radius, the Jacobian, the theta, the r, and this is equal to 2 pi times the integral blah blah in the r, which is equal to if you do that's just a polynomial, you get 2 pi divided by 3. That's our volume. I wonder if there are. Okay. Let's see the number 23. So we want to find the volume lying inside both the sphere, of equation x squared plus y squared plus z squared this, and some cylinder. The cylinder x to the power of 2 plus y to the power of 2, this, right? Wait a second. Ah, no, that's the, okay, so sorry, this was, no, this was the 22. 23 has here, and this there is a 2 apparently, yes. Well, you can try to do the 22 too if you want. So what do we have here? We have some sphere. X, Y, Z. The sphere is centered at the origin, and radius is, so radius is the square root of 2 times a, while the radius of the cylinder is just a. So the cylinder lies completely inside the sphere, right? This is the cylinder. So we will have, the interesting part is what is inside the cylinder and inside the sphere too. So we have two sections. So everything is inside here, we care. Okay. All right, so let's see what do we get. Our volume will be, the volume here, it is symmetric with respect to the xy plane. So I can write 2 times the integral, and the domain is the usual domain, the disk. And then we have the sphere function, which is 2a squared minus this, right, in dx dy. We have to solve this integral. So what do we get? So we do the polar coordinates, we have 2 times, and then here we have 0, a, 0 to pi, again p coordinates. And this is the square root of 2a squared minus the radius squared. We are lucky because there is the Jacobian here that saves us d theta dr. So this is equal to 4 pi times integral between 0 and a of this function in dr. And this is 4 pi times minus 1 divided by 3 times 2a squared minus r squared to the power of 3 halves between a and 0. And if you do the computations, you get this is equal to 4 pi divided by 3, a to the power of 3 times 2 square root of 2 minus 1. That's the volume that we were looking for. Okay. All right. Let's give a look to the 25 to just, okay, I have just 5 minutes, so maybe I will just state the problem. 25 is find the volume of the region lying inside all the 3 circular cylinders. So find of the region lying inside all 3 of the circular cylinders x squared plus y squared equal to a squared y squared plus z squared equal to a squared, and x squared plus z squared a z squared equal to a squared. So this is rather tricky to figure out what's the shape of this. I'm not even sure. I think I can't draw this object. I suggest you to try to make a sketch like using some software, because it's very hard to try with GeoGebra or Wolfram Mathematica or Wolfram Alpha. It should be something like this. So if I focus on the first octant, we do get something like this. This is one cylinder, right? And then I have another cylinder here. Well, portion of a cylinder. And then I have a third one here. No, like this. Right? So the intersection should be something like this. So yeah. Um, yeah. So the intersection will be the collection of all these yeah, of all these pieces. If you look at it from above, maybe um, I guess you could see, no, you could see I mean something like this. You have cylinders, and underneath this should be this piece here. Uh, Maybe we'll call something like this. Well, one slice, but I want to use that slice because the final volume will be um, 1, 2, 3, 4, 5, 6, 7, 8, and then we have the below part, so it's gonna be 16 times the volume of the red part. So the volume, the seeked volume will be 16 times the volume of the red slice. Okay, I have no time to conclude it now. We can take it from here in 15 minutes. So see you in 15 minutes at 11:15.
Hello?
Yes?
Yeah, sorry, just a quick question. In 50 minutes, right?
Yes.
Okay, because I was wondering on the X, I didn't understand if he mean the only first octant or all the octant.
All the octants. That's the
Okay,
intersection between the three cylinders.
okay, then I know, thank you.
No worries.